Welcome to this explainer. You know, if you've ever looked at network engineering and felt like you were just staring into a giant bowl of technical alphabet soup, you're absolutely not alone. Today, we're going to map out all these complex, abstract concepts by comparing them to something we all intuitively understand, a bustling modern city. Think of it as our digital metropolis. Okay, let's dive right into this.
Here's our roadmap for today. We'll look at building the digital city, directing the traffic, managing the network flow, securing the borders, and finally, the future of networks. Let's see how all these pieces logically fit together.
Section 1. Building the digital city, the foundational infrastructure.
So, the OSI model. This is basically the blueprint of our metropolis. It perfectly illustrates how all data transmission is structured. It ladders up from the raw physical cables at the very bottom, up through logical addressing and error checking in the middle, all the way to the application layer at the top, which is where we actually interact with the software. It's the foundation of everything.
Now think about it. Every single device in our city needs a unique numeric address just to be found, right? For the longest time, we used IP4, which gave us a 32-bit address space. But just like a rapidly expanding city running out of zip codes, we literally just ran out of room. That's exactly why the massive 128-bit address space of IPv6 became absolutely necessary. We had to ensure every single new device gets its own unique location on the map.
Okay, so what actually connects these addresses together? Let's look at two foundational pieces of hardware. A switch operates at layer 2. You can think of it as managing the local streets. It uses permanent 48-bit MAC addresses, which are hard-coded directly to a device's network card, to switch data frames locally. A router, on the other hand, operates at layer 3. It uses IP addresses and routing tables to route data packets across entirely different neighborhoods and external networks.
Moving on to Section 2, directing the traffic, getting data to its destination.
First up, we need to understand how data actually speaks. It's kind of like using a megaphone in the city square. We have three main types of traffic here. Unicast is a direct one-on-one conversation, one sender to one recipient. Multicast is more like a targeted group chat, where one sender is talking to multiple specific recipients. And broadcast, well, that's just one sender shouting a message to absolutely all the devices on the local network.
But how do devices actually know who they're talking to? Imagine manually assigning an address to every single resident in a massive city, and then keeping a physical ledger of where everyone lives. Total chaos, right? Thankfully, we have these protocols to automate the city's directories. DNS acts as the city phone book, translating those easy-to-remember website URLs into numeric IP addresses. DHCP is your automated city registration. It automatically hands out IP addresses to prevent conflicts. And ARP? That's the local mapper, linking those logical IP addresses directly to the physical MAC addresses on your local network.
So the crucial point here is that IP addresses are incredibly valuable real estate. We can't just waste them. That's why subnetting, CIDR, and NAT act as our digital city planners. Instead of wasting that valuable public space, these tools divide up large networks and actually allow many internal devices to share a single public IP address. By managing this space efficiently, these systems conserve addresses and keep the internet from completely running out of room.
When the data actually hits the road, it chooses one of two delivery services. On the left, we have TCP. This is like certified mail. It's connection-oriented, highly reliable, and guarantees that every single package arrives in order with zero packet loss. On the right, UDP is, well, it's like throwing a handful of unverified postcards into the wind. It's connectionless, it's unreliable, and packets might arrive completely out of order or get lost entirely. But here's the catch. It is incredibly fast, which makes it absolutely perfect for things like live streaming, where speed matters way more than perfection.
Now, what happens when data needs to leave town? Well, it travels out through the default gateway, which is that single router acting as the main highway out of your local network. From there, dynamic routing protocols take the wheel. OSPF acts like an advanced GPS, mathematically calculating the absolute shortest path to save bandwidth. Or we have BGP, the Border Gateway Protocol. This one directs data using complex, policy-based routing rather than just hunting for the shortest route.
Section 3, managing the network flow, keeping the city moving.
You know, one of the best ways to beat network congestion is load balancing. Think of this as the city's traffic cop. When links are handling way too much data, it distributes the load so no single server gets overwhelmed. Traffic can be handed out sequentially using a round-robin method. It can be weight-based, distributing based on the actual capacity of the servers. Or it can be based on response time, where it just automatically sends data to whichever server is answering the fastest.
But let's be honest, all traffic isn't created equal.
We've all been frozen mid-sentence on an important video call just because someone else on the network decided to download a massive file, right? That's exactly where QoS, or quality of service, comes in. It prioritizes critical applications, like voice and video, over simple file transfers. MPLS, or multi-protocol label switching, helps make this happen by directing data using short path labels. This significantly improves performance and supports that critical traffic engineering so your meetings actually work smoothly.
All right, Section 4, Securing the Borders, Protecting the Digital Metropolis.
Now, what's really interesting about this next concept is how we handle external threats. To protect our network, we create a literal no man's land. A DMZ, or demilitarized zone, is a specific security mechanism that acts as a strict buffer zone between our private network and the public internet.
As you can see, this buffer zone is all about isolation. If you have servers that absolutely have to face the public internet, like your company website for instance, you place them right here in the DMZ. This ensures that the unpredictable, highly vulnerable public internet is kept completely isolated from your sensitive, secure, private network. Backing up that buffer zone are the city's true border guards. First, we have firewalls. These are the security devices that filter incoming and outgoing traffic based on strict, predefined rules. Then, proxy servers. These act as intermediaries, hiding your internal client IPs for privacy and giving you an added layer of security. And finally, VLANs. Think of these like security doors. They take a physical network and divide it into multiple logical ones, which really helps restrict malicious traffic and control access to your systems.
But what if you're working remotely, completely outside the city walls? Well, then you use a virtual private network, or VPN. A VPN creates a secured, encrypted private tunnel right over the inherently unsecured public internet. Whether that's a remote access VPN for an individual employee, an SSL or IPsec VPN, or even a site-to-site VPN linking two branch offices together, it gives you a safe path through the chaos of the public web.
Section 5, The Future of Networks, Modernizing the Metropolis.
Let's see how all this builds into the future. To support modern architecture, we are rapidly transitioning to IPv6 using methods like tunneling, which actually encapsulates IPv6 traffic right inside older IPv4 packets, and dual stack, where we run both protocols simultaneously. But the real game changer here is SDN, or software-defined networking. SDN actually separates the network's control plane from its data plane. Instead of manually configuring hardware, a centralized software controller provides APIs for applications and continuously monitors everything.
This programmable capability leads us straight to the ultimate goal, the autonomous network. Through network automation, we're automating provisioning, configuration, and testing. This massively reduces human error and operating costs. Hand in hand with that is zero-trust architecture. In this modern city, absolutely no user and no device is ever trusted by default. Every single resident is treated as a potential suspect until verified.
Which leaves us with a genuinely fascinating paradox to consider. The digital metropolis is more capable, more automated, and more heavily fortified than ever before. But if these networks now provision themselves, heal themselves, and inherently trust absolutely no one by default, who is really in control of the digital city? Thank you so much for joining me for this explainer. I hope it's helped illuminate the complex yet beautifully structured world of network engineering.